Titrations are a common laboratory technique for measuring the concentration of solutions, and as you might guess, calculating a concentration is one of the most frequent types of calculations you'll perform with the data. For the examples for today, I'm going to talk about titrating an acid and a base, and we're going to put the acid in the Erlenmeyer flask, and we're going to put a base solution in the burette. The specific analytes don't matter, but there's sort of two flavors of titrations that we'll talk about. The first one is a standardization titration. In this one, we're going to use a standard, a known amount, and with it, you're going to determine the concentration of the titrant, in this case, the base. Standards are chemicals that we have in the laboratory that are very stable and are well characterized. We know the concentrations or the purity, and therefore they're useful for checking the concentration of chemicals that might not be as stable in storage. The second type of calculation is an unknown. And this is one where we know the concentration of the titrant, and we're using that to measure the concentration of the analyte, where the analyte is unknown. And so you're going to look for this in the wording of the problem, but I have one example of each to go over today. So again, we have our sodium hydroxide, our base, in the burette. And in this case, we have the KHP, the potassium hydrogen phthalate, as a standard in that Erlenmeyer flask. And so the problem is sodium hydroxide titrant, that's the stuff in the burette, is standardized using potassium hydrogen phthalate. So standardized is that process of measuring the concentrations with one of these titrations. So what is the concentration of titrant? If we have 0.7251 grams of KHP. And it isn't pure, this is grams of standard, and the standard is 92.94% KHP. We know that the volume of titrant is 42.11 milliliters, and we're trying to determine the concentration. When you set up these calculations, you want to start with the chemical that you know and head towards the chemical you don't. So what I'm interested in is heading towards moles of sodium hydroxide on the right there. That I'm going to use later to put in a calculation where I'm looking at the concentration of sodium hydroxide, and I want the amount of the solute, in this case the sodium hydroxide, and the amount of solution. To get to molarity, I'm going to want the solute in moles, and there's my moles of sodium hydroxide. I'm going to start with the amount of standard. Now in this case, that's an amount in grams. Anytime you're looking at two chemicals, you should be thinking that you're going to use a mole-to-mole conversion. So I'm going to take the moles of KHP and use the balanced chemical equation to change that to the moles of sodium hydroxide. And then we're left with connecting the grams of standard to moles of KHP. And the little trick here that might be easy to overlook is the molecular weight will let us get from grams of KHP to moles of KHP, but we need to use the mass percent, the purity, to get from the grams of standard to the grams of KHP. So my grams of standard in this problem was 0.7251 grams. My first conversion is using the purity, so 100 grams of standard goes to 92.94 grams of KHP. We need the molecular weight of KHP, which I didn't put in this problem. You can look it up. But it will be at 204.22 grams is equal to 1 mole. And this is 1 mole of KHP, and I need to be careful. I can't put that in my calculation of the concentration of hydroxide. I need to do one more step to go from moles of KHP to moles of sodium hydroxide. And looking at the balanced chemical equation, 1 mole of KHP is 1 mole of sodium hydroxide. So this comes out to be 0.0032999. And I see 4 significant figures, both for the mass and the purity. And the units were moles of sodium hydroxide. So this is how many moles of sodium hydroxide had to come out of the burette to completely react with the potassium hydrogen phthalate in the flask, as indicated by the phenolphthalein changing colors from clear to pink. So I'm going to go ahead and put that amount as my solute. This is the moles of sodium hydroxide. And my amount of solution is that volume of titrant. Okay, I want the concentration of the titrant, the moles in the titrant I just calculated. The volume is how much I had to add, how much contained that number of moles. So 42.11 milliliters. And to get to molarity, I need to change those milliliters to liters. And I get 0.0783641 moles per liter now, moles of sodium hydroxide per liter of titrant. And I'm still looking at 4 significant figures, both from the previous problem and the 4 significant figures in that volume of titrant. And so 0.07836 molar would be the answer to this problem. So this is a standardization titration. We have a known amount of standard. We're determining the concentration of titrant. Typically, after you do that standardization titration, you'll use that standardized titrant to measure the concentration of an unknown. In this case, the unknown is going to be sulfuric acid. And we have our sodium hydroxide in the burette. So what's the concentration if I have 25.00 milliliters down here? The concentration, I don't know. Up here, we required 38.96 milliliters of that titrant dripped in before the phenolphthalein changed color. And the concentration we determined on that previous slide, 0.0783641 molar. And I'm going to leave the extra digits without rounding to avoid rounding errors. So again, here we're trying to determine something about the sulfuric acid. I'm going to need to go to moles of H2SO4. And I'm going to start with that volume of sodium hydroxide, so milliliters NaOH. Anytime you have 2 chemicals, look for a mole-to-mole conversion using a balanced chemical equation. And the pattern of going from milliliters to moles, you're going to use molarity. That's going to let me go from liters of sodium hydroxide to moles of sodium hydroxide, and just a simple SI prefix will get me from milliliters to liters. So be careful here that you're using the volume of the right chemical. So the volume of sodium hydroxide is that 38.96 milliliters. You don't want to use the 25 here. 1,000 milliliters, 1 liter. 1 liter, and the way we put a molarity in here is we break apart moles per liter. So if this is moles per exactly 1 liter, then for 1 liter I have 0.0783641 moles of sodium hydroxide. Finally, I'll use the balanced chemical equation to go from moles of sodium hydroxide to moles of sulfuric acid. And I need to go to the balanced chemical equation to get those coefficients, but 1 sulfuric acid is 2 sodium hydroxide. So 1 mole of sulfuric acid, 2 moles of sodium hydroxide. And I have 0.0015265 moles. I still have 4 significant figures, both from the concentration from the previous slide and from that volume of titrant. So this is the moles of sulfuric acid that were required to completely react, moles of sodium hydroxide, moles of sulfuric acid that were in the flask that required 38.96 milliliters of sodium hydroxide to react. So if I want the concentration of the sulfuric acid, I need the solute over the solution. So this is the 0.00152653, 4 sig figs, moles of sulfuric acid. And now I want the volume of that sulfuric acid solution, that 25 mils there. To get to molarity, I need to change that milliliters to liters. Now I have moles per liter or molarity, and 0.0610613. Again, 4 significant figures have carried through. This is now molar H2SO4, moles per liter. And so that becomes 0.06106 molar is my answer. Okay, so in this case I had a volume going to a concentration. In the previous case I had a mass going to a concentration. You can do it either way. And that's a basic setup of a standardization and an unknown titration.